Hi, good morning, everyone. My test sound clear. Please raise your hand. All right, so we start down now, huh? So don't want to. Okay, so attendance getting worse. Okay, expected because I think quite numbers of you this morning having a tuition class. All right, so never mind, later I will share the recording videos. So just want to remind you, okay, so this online class I not going to just finish for today or maybe tomorrow another class or how. Okay, I will continue conduct I think maybe twice a week. Right. So or let us see how first. No, twice a week, maybe 2 weeks once. All right. 2 weeks once. So because of the when I checking the wins again, so we definitely have not enough time to cover our syllabus. Right. So especially before the trial. So the trial is confirmed. Okay, so trial is confirmed if there's no any change after this. So it will be finished before the second term's holiday. All right, so it will be much earlier than my planning. So I think I at least have to cover the last two chapters online. Okay, okay, this is the first thing, and then the second things there will be the streamings for your classes, right? So I think the list the teachers was sent in. I was saying also lah. Okay. Anyway, your last year form teacher was sharing in the class. I think by Saturday night, if I'm not wrong. So there will be the three classes involved lah. So three of you, right? The Benji's, Simon, and Charles. So there will be the quite numbers change here. Right? So there was some go from Francis to Simon, Simon to Francis, and then Simon to Charles, Charles to Simon, something like that. Right? So just wait for that. And then basically your classroom, okay, your classroom as I sent into a group already, so remaining as your last year class. And for the class Francis, last year your points connection point have a problem for projector, right? So I already changed it the cable, so later on in your class shouldn't have a problems anymore lah. Right, so no need to worry. And then 5 inches you will move to upstairs or 5 inches or no, okay, it's downstairs. So don't worry lah. So all this classroom problem is have been settled lah. Right. Okay, so we continue from the lesson previously. Okay, so remember when the question asks about the light energy, so please remember the light energy formula. Okay, which is the E equal to the SF. This is a Planck constant here. On okay, so E equals to SF. Okay, and this formula, right? It will be made equal to the Hc over lambda as well. Okay, because F equal to the C over lambda. Right? So from the formula that we learned, okay, last year V equal to the F lambda, and then we make the V as a speed of light in the vacuum, which is a C. So that's why when we rearrange the equation, we came to this one. Okay, and then this one, the powers. Okay, the power. Okay, so from your general science, you should know that power defined as a rate of energy per time. Power defined as a rate of energy. Okay, and in this case, when we change the formula, energy will define. So sorry, no need to define energy anymore. Okay, so power defined as energy per time. So we substitute the energy formula here, which is energy equal to S5. Okay, Planck constant multiplied frequency over the time. So, and then after that, okay, we also energy is also equal to the Hc over lambda. Hc over lambda, so that's why we have the lambda over time. But then after that, it changes it as N Hc over lambda. So from here, what you should notice here is this N, the N here actually used to presenting 1 over time. So from this formula actually is what? N is defined as a 1 over time. Then 1 over time here is not the frequency that we learned as a 1 over period. No, it's not like that. This N 1 over time is defined as what? Defined as a numbers of proton per second. Okay, so this N number of photon emitted per second. N equal to 1 over T. It defined as a numbers of photons emitted per second. Alright, so when the question asks numbers of photon emitted per second, so you should know that this is looking for N. Usually, when we use the formula N, it's just an integer. It's just an integer to define a numbers only. Okay, but in this case, this number is numbers of photon, but it's not just numbers only. It's specifically referring to the numbers per second. So it means each second how many numbers of photon. Right? So this is something that not state very clear in the formula itself. Alright, not state very clear in the formula itself because it suddenly told you power defined as NHF. So student having a problems to understand from the fundamental concept, which is power defined as a rate of energy, right? As I told you, as I show you here, this one. By right, it should explain this one, and then from here, it should explain that the N is defined as a 1 over T, which is the numbers of photons per second. So at least the concept about the time that involved in the rate of change of energy is still there, right? But there is a incompleted explained in the textbook. So I hope that you can edit this one for understanding about this one, numbers of photon being emitted per second. All right, and then the rest is a substitution formulas lah. All right, so basically this chapter, because it's a totally new chapter, all right, so the formula is similar like what you learned in the last year chapter 3 gravitations. So you need to know how does formula from one formula express into the other formula. Okay, and then to solve the problems, it's a substitution based on the information provided, substitute in the formula, then solve already. For the calculation part, it's very easier. Only the challenging part is they're not ready straight away apply the formula provided in the list. Most of the time, you need to express the formula. You need to express the formula, then only you can solve. Okay. Like happens in this year, right? Okay, I'm not sure that I have discussed about this or not. Happens for this year SPM. Yeah, the SPM is just over. There's one problem here. Where is it? Okay. So there's one question. The question become one problem for the student. Everyone complains, say that the information is not provided. Okay, for this gravitation questions, which is a question asking about the linear speed. So most of students, when talking about linear speed, they will look at this one, linear speed. V equals the square root of gm over r. So the problem is that questions only provided r, and then g is a constant value. So they're having a problems about this mass of the Earth. They in the question itself doesn't provide mass of the Earth, and then some students that have memorized it. So the student apply what they memorized about the mass of the Earth. So I do believe for those students really remember, memorize the mass of the Earth, and then they substitute based on this formula, they solve it, I think they will accept. But anyway, this part I'll find out with my friends, those marking the paper, right? But I don't believe they will accept for this one. But and then after that, they keep complaining. They say that information is not enough, so they cannot solve it. But actually, they forgotten already. We have another linear speed, which is this one. We have another linear speed formula also, right? And in this case, R provided already, so you can substitute here. And the T is not given, but actually the T is not given directly. It's already mentioned that satellite is a geostationary satellite. Geostationary satellite means the orbital period is 24 hours. That is the knowledge that you should know the difference between the two different types of satellite, for the geostationary satellite and the non-geostationary satellite. So that is something that you should know about the type of satellite. So when it told you there's a geostationary satellite, means the orbital period is 24 hours. Then you substitute 24 hours. Change it into the unit second, then you can find the linear speed in the unit meter per second. So that is the challenging part for the chapter 3 and also chapter 7. Right? So you need to know how to apply formula. Right? So hopefully you learn about this one. Just like when you look at the formula provided for this chapter, chapter 7, you see here, right? So this one we learned already. This one actually is the same as given in the wave here. Here V equal to F lambda here, this one. And then just only change V as a speed of light. So and then rearrange it become this one. So this one actually repeated. Right. Then after that, next what we're going to learn is this one. Lambda equal to the H over P. What P is it? Is it the power? So when you compare these two formula, what you know? What is this? Anyone can tell me what is that? Please comment. What is the P stand for here? Is it the power? Power is here. There is a power here. I just finished discuss about this power, and then N is the numbers of photon per second. Right? And then this one also the speed and the energy of light from the F here substitute, then become the Hc over lambda. And then after that, okay, so the F also can be substituted here. Change it to the other formula because of the N has C over lambda. Alright, so now anyone can tell me what is the P stand for here for the formula 3 and 4? Anyone can comment? Or on the mic, please answer my question. The P here stand for what? Is it the power or what? Right? Yes. Okay, thank you for the Yushan. So P here actually is momentum, because from this formula 3 and 4, you can see P actually after that substitute as what? Substitute as a mv. As you know, the product of the mass multiplied velocity here is the one concept you learned in the last year, chapter 2, momentum. So P here is momentum. Right? So why suddenly involve momentum? You see, we're talking about momentum, it must have the mass, which is a momentum referring to the particle. It must have the mass, particle. So it referring to the light behave like the particle. At the same time, it also involves the lambda. Lambda means that is the properties for the wave. Lambda is a wavelength. So this formula is the one suggesting light behave with the duality, wave particle duality. Wave particle duality. That is what we're going to learn next. Okay, here this is another substitution of a formula for the example here. Okay, so as what I said, that you need to learn flexible, apply with the information given, apply the formula. Not that directly pick from the list. You pick from this, and then you have to be smart to express the formula. Right? If you pick from the list, you only have a P power as an N has F. But here, it's providing the wavelength, it's providing the numbers of photon. Here you have this number of photon you have here. Planck, H is a Planck constant. So it doesn't have a frequency, but you have the given the wavelength. So that's why you need to change the frequency as a C over lambda. So C is a constant radius sphere. So there's an example to let you learn that you need to express a formula. Okay. And here is involved about the efficiencies, right? So when you involve efficiency, you apply the efficiency formula. Efficiency formula, which is the power out over the power in, multiply 100%. So since it told you there's a 10% output, okay, it's used to emit photon. Here, this number of photons. So you need to know here what is the average wavelength in the nanometer, right? So 10% of the output power, 10% of the output power of 100 watt. So 10% for 100 watt is only 10 watt, right? So in this case, there are right. So this is so means that you're looking for the output power, right? So output power is 10%. Then you just based on the simple form calculation, you can find the output is 10% is 10 watt, just like that. No really need to apply the formula lah. Right? It's just a basic concept. Then the rest, make this power equal to the formula, then you solve it. All right. So for this formula practice 7.1, right, you can try to do. I no need you to write the how to say that the question here. So later when you come back to school, I will give you this handout for the worksheet. Then only you do that. All right. So now we're talking about the photoelectric effect. Okay. Actually, to discuss photoelectric effect, it will be easier if we have go through the chapter 5. Because in chapter 5, we learn another one process. We call it thermal emissions process. Thermal emission process. So these two process, thermal emission process and the photoelectric effect is similar. It's similar but not the same. Right? It's quite same. The concept why it's similar but not the same means that both of them talking about emissions of electrons. Emissions of electrons. Both of them, we're looking for the emissions of electron. Just only that this emissions of electron is different way. Right? So for the photoelectric effect, it's talking about okay when we illuminated a means of light on the metal surface, the metal surface were able to emit the electron. So that's why you look at the light game here. Very easy to understand. So when you have a source of light hit on this metal surface and then the electron emitted. So this process or this effect of the electron emitted due to the light, okay, you may say that it's shooting, or actually we use the term is illuminated, okay, on this metal surface, the electron emitted. So this effect we call it photoelectric effect. So before we further discuss about this, is there anyone can tell me when you look at this light game, it seems like application about what? For this thing, application about what? Anyone can try to guess, or maybe you study already, you can tell me. At the end, actually, this one is a very important application for what? Nowadays is quite widely used in Malaysia, right? So it's about what? When you have a source of light hit on the metal surface and then electron emitted. So we use it for what applications? Anyone got any idea? I think that's the main reason why this chapter is put into your syllabus. Because this is one of the important applications in your daily life now. It's a concept that relates to the green energy. Anyone got idea? Yeah, it's about the solar panel. Okay, it's about solar panel. So because the solar panel, right? So when we let it face to the sun ray, So electron will be emitted on the surface, and these emissions of electron, we use it to generate the electricity. We use it to generate the electricity, because electricity we need electron to flow, right? So we need electron. Once the electron can flow, then we get the electric current, right? So, but to let the electron flow, we need the power source. Example, okay, we need the battery. Only battery provided the electron motive force, then the electron can flow, then we get the electricity, right? Or from the generator. Generator, that one you will learn in the chapter 4 later. Generator, how we generate the electricity, okay, from the rotations of the tube. Okay, because the rotation, it will make the change of magnetic flux. All this you will learn in the chapter 5 later, don't worry lah. Right. But other than these options, what are the options that we can emit electron and let the electron flow? That is the one, photoelectric effect. Okay, for the solar energy. Right? Okay. So, but the problem is this photoelectric effect, it have the term and condition. What term and conditions here? As you can see here, it must be, the light must be at certain frequency. Must be at certain frequency. Then only the electron can be emitted. What's meant by certain frequency? Okay, so previously when we learned about the electromagnetic spectrum, we already know that different range of the frequency, the visible light itself, okay, it will be divided into the different colors, right? So that's why they have the certain frequency, and then also the metal surface only fulfill the certain frequency, then only the electron can be emitted, right? So there's one of the important criteria or important rules. Maybe it's a rules from the experiments show that no any kind of light get able to emit the electron when we emulated it on toward the surface, metal surface. No any kind of light. So that's why here you see there is a characteristic of the electron photoelectric effect, right? Characteristic of the photoelectric effect. So when the question asks, definitely will be focused here lah. Okay, so when the light sensitive metal surface, so this metal must be the light sensitive metal surface lah. So what kind of metal is a light sensitive metal? So far at the end of this chapter, you got show you the two example of the material, the metal sensitive with the light, right? So but you don't need to learn really detail, right? Why this metal is not sensitive with the light, why this kind of metal is sensitive with the light. That one you don't need to learn. That is not involved in your syllabus cover, right? That one will be go to very deep already, right? So in your syllabus, you just need to know about the two example. I think by the end of the chapter here, so it will show you two example like this one. Okay, so we have the lithium and we have the calcium, right? So these are two example the method here. Okay. Calcium. CAESIUM. Cesium. No calcium. Cesium. Okay. So there is an example of the light sensitive metals. Okay. So and then it must be the cathode. We cannot attach this one as an anode because it's going to emit electron. So for the surface that the metal surface that emit electron, it must become the cathode. I think this part is very clear when you learn chemistry, especially when chemistry when you do the example like the electrolysis. So you want to determine which metal is a cathode and not, right? So you have to observe. Then belum belajar in Form 5 so later you will learn also lah. Okay, so to determine which one is a cathode, act as a cathode, act as an anode. So we need to know, okay, the electron direction. Where is the electron flow? So in the case, you're going to connect in chemistry. This one is talking about chemistry, because in chemistry you have to connect these two metal with the galvanometer. When the galvanometer deflect from the direction where the galvanometer point deflect, then you will know the direction of the electron flow. So from that, you will able to determine which one is the anode, which one is the cathode. Okay. Galvanometer is a device similar like the ammeter and voltmeter. Only the difference is galvanometer, the pointer point at the center. Center is a 0. So it means that you got the negative reading and positive reading. So when the pointer deflect to the left hand side, from the center deflect to left hand side, means electron flow from the right to left. So if the connection here toward this metal root and the connection here connect toward this metal root, means that here is a cathode, because the electron flow from this metal root to the right hand side, left hand side metal root here. So it means that here's a negative, this is a positive. So there is a way how we know about the cathode and not in your chemistry. But for physics, it's very simple. As usual, physics always easier than chemistry. All right. So because we're talking about the photoelectric effect, means that the electron is emitted from the surface. So automatically, that method is our cathode. So that's why bracket here, there's a cathode. So it's illuminated with a certain light means. Electron will be emitted from the metal surface. Those electrons are called photoelectrons. We call it photoelectron. Why is photoelectron? Because it's the electron emitted due to the light source. Light source have a light particle, which is we call it photons. Okay, and this light particle photon have energy. That's why we call it light energy. All right. So or photon energy also can. And the electron emitted due to this light energy, we call it photoelectrons. Right, it's very simple. Okay, photoelectron. Okay, and another one thing that you may learn about this, why this light sensitive metal, it must be in concave surface, concave shape like this. As what I learned last year, chapter 6, for the concave mirror, it will be converts the light. So same also when the electron emitted from this concave metal shape, then the electron will be converged. So converged to the anode. So it means the anode, it should be placed as the focus point, principal focus of this concave shape. But in your chapter 7 in your syllabus, they not really discuss about this because it's mixed with the concept that you learn in the chapter 6. So I explain it here so that you will know why it must be designed in that shape, that I can draw in that way. All right. So we need to enlarge. We need to enlarge the surface to receive the light source. At the same time, we need to focus this emitted photon electron emitted, so that we can have the more numbers of electron can be flow in the circuit. The highest the numbers of electron can be flow, the rate of flow is higher, then the higher the currents. Right. So because in the chapter 3 later, you will learn current defined as the rate of the charge flow. And this rate of the charge flow here, the Q is based on the numbers of electrons per time. So that's why we need to concentrate all the electron emitters so that it all will be go to the anode. Then it will continue flow in the circuit here. So the more numbers of electron can be flow, the higher the current I will get. Right? So I use a mini ammeter to study the result. All right. So the connection of battery here to make sure that is this one become the cathode, this one become the anode. Right? So that is the purpose of connect the battery here. Okay, and that means that it must inside the tube here, inside this tube here must be the vacuum so that there's no any A particle will be collide with the electron, let the electron deflected into the other direction. So that's why inside must be the vacuum. All right. So all this is a part of the knowledge that you learn in other chapter. So it's not really discussed in the specific in this chapter. So but you still need to know why. Okay. So I already highlighted for you so that you know all the design here. Okay. Then you see, we still talking about this certain frequency. Okay, and then the emitted photoelectron are attracted to the anode, which has positive potential. So the movements of the photoelectrons from the cathode to anode, okay, it will produce a certain a current. It will produce currents inside the circuit. Okay, so why it able to produce a current? I already told you just now, because the current defined as the rate of the charge flow. And then the electron itself, numbers of electron itself, it will get the total charge over the each second that is defined as a current, right? So each electron have a constant charge. Each electron, okay, have a constant charge which is equal to 1.6 times 10 to the power of negative 19 coulomb. That is a charge of an electron. Okay, 1.6 times 10 to the power of negative 19 coulomb. All right. Okay. So the formula still back to the previous formula. Okay. From here we have the electrons. Okay. Sorry, not electron. We have the light energy equal to Hf and the lambda equal to h over p. So the p here is the momentum. So the involved constant. How can the value of the h can be determined in the lab? All right. So this is the way we determine the Planck constant. All right. So later I come back this one. Okay, so this one later I will come back. Okay, suddenly came out this formula, right? So don't worry, later I'll come back. So now I'm talking about this one, the characteristic of the photoelectric effect. Okay, so photoelectric effect occurs, okay, when the light straight on the surface of the metal, which is a light sensitive metal. So the electron in the metal itself, metal is a conductor. So why metal is a conductor? Because the metal have a mobile electron. Okay, so this mobile electron in the metal is not, it cannot be simply emitted from the metal surface, but it can use a conductor to conduct electricity. So it means that if we use a metal connecting complete our circuit, right? Then the mobile electron, due to the power supply that we given, it will force the electron to be flow in the circuit. Then we get the electric current. But now the issue is we don't use it in the part of our connection circuit, okay? Because inside the tube they have broken between the cathode and anode, so there is no connected. Then we want to force the electron emitted from the cathode, and then it can be moved, get escape from the surface, and then accelerate towards the anode. Right, so that is a concept to get the emitted electron from the metal surface. Right, so this effect we call photoelectric effects, right? Okay, so according to the classical theory, as I told you, the light in wave is is in the form of the continuously spectrum, continuous energy. Right, so photoelectric effects should be able to occur at any light wave frequency, by right? According to the classical theory, okay, because classical theory is see that the light wave as a continuously spectrum. Okay, so by that it should be able to occur at any light wave frequency. Okay, so the bright light which have a higher energy should able to emit electron quickly. Okay, so this is very important. Bright light, as according to the concept, brighter the light, higher the energy, right? This is very general concept, right? Okay, so brighter the light, higher the energy. By right, according to this, it should be able to emit more electron or quickly electron. Quickly, right? So dimmer light have the lower energy, so need longer time to absorb enough energy to escape from the metal surface, according to classical theory. Right? So, however, the result of the photoelectric effect experiments show that the emission of the electron only apply to the light with the frequency that exceeds a certain value. So, and that is without affected by the intensity of light. Without, remember this one, without affected by the intensity of light. So, the meaning here is according to classical theory, higher the brighter the light, we got more energy. Higher the energy, it should able to let the electron absorb more energy. Once the electron absorb enough energy, it will escape on the metal surface. So the meaning here is, if we provided the brighter light, then the electron emitted from the metal surface, it will be faster because it will be absorbed enough energy, then it will go, it will emit it. But right, the concept should be like this, according to classical theory. But the experimental result showing that it's not work in the way. If you, let's say, you given the one source of light with a particular frequency, and then the lights is very, very bright. So no matter how much you increase the brightness for this lower frequency or certain frequency bright the light, you let it straight on the metal surface. No matter how long you wait, it still have no any electron can be emitted. So it means that this is something wrong according to the classical theory. Then when the scientists continue do the research, they notice that no matter I use the brighter light or the dimmer light, they notice that brighter or dimmer light, when they're adjusting the frequency, changing the frequency, finally they notice that when they reach to the certain frequency, immediately they got the electron emitted. So it doesn't depend on the brightness. It depends on the frequency. It depends on frequency. So, and then it's immediately. That's why I said that photoelectrons are emitted instantaneously. Instantaneously means that it's at the same time, no gap of the interval time. Right? The concept, the term that we use here, instantaneously, is a concept that even faster than immediately. Right? So it can say that no gapping time. Right? So for those light frequency, even at the low light intensity means that dimmer light. Right? So from here, it's showing the concept. Very important here is photoelectric effect is the effect to emit electron from metal surface when we strike the light towards the metal. And in this case, it doesn't affected by the brightness. It is affected by the frequency. All right. So that's why that is become the really important characteristic of the photoelectric effect. First one, when you given the higher frequency, it will affect the kinetic energy of photoelectron. Right? So photoelectron can be emitted faster. Right? So, and then the minimum frequency of the light to emit the electron, to emit these photoelectrons. If you want the better terms, you can use that emit photoelectron. So this frequency, we have a name, we call it threshold frequency. And then the symbol is F0. So different metal have the different threshold frequency. Right? Different metal depends on how it's sensitive towards the light. It have their own threshold frequency. So it means that for this metal A, when you given this frequency, electron emitted. But it doesn't mean that it still work on the different metal B, because different metal have their own threshold frequency. Okay, and then the kinetic energy of the photoelectron does not depends on intensity of light. Kinetic energy of photoelectron does not depends on the intensity of light. Okay, so means when you increase the light intensity, it's not going to produce a photoelectron with a higher kinetic energy, right? So this is something that you need to remember. Right. So means you want to increase the photoelectrons kinetic energy, you need to increase the frequency. You need to increase the frequency. All right. So please remember this part. Okay. Another one, not good in this textbook explanation is especially when you go to the last, very last sentence in this chapter before talking about the characteristic applications. When you look at this very last sentence in the page 243. Right? The last sentence here. As the light intensity increase, photoelectric currents in the photocell circuit also increase. Right? So when the teacher not highlight about this sentence and it's no highlight the explanation, what's the meaning here, when the student learn read by themselves, you may confuse here. Right? So because I 2 years already, I noticed that the student were confused. Teacher, you told us photoelectric effect doesn't depend on intensity of light. Why here it told us the intensity of light increase, it will increase the photoelectric? What happens here? So be careful. Here is talking about what? Here talking about photoelectric currents. Okay. So please make own notes here. I explain again here. Actually, this is a two different thing. Okay, where is it? Okay, this part is keyword. This one is 7.3. Later I come back this one. So no wonder why I didn't talking about the momentum. Okay, this part I accidentally skip. So later I come back. Okay. So here. Okay. Okay, see here. So to to emit the electrons, to emit this photoelectron, we need the at least must achieve the threshold frequency. So after that, if you given the frequency more than the threshold frequency, which is this frequency of light is more than the threshold frequency, so this electron will be emitted with a higher velocity. So that's why the electron have a higher kinetic energy. So this part actually is still fulfilled. It still fulfill that conservation energy concept, the principle of conservation energy, because when the light source have higher frequency, means that the light have higher energy. And this higher energy of light source, it will be let the electron emitted with the higher kinetic energy. So from the high frequency wave, high frequency light, which is a high energy, then it will increase, it will convert it as a kinetic energy, so the kinetic energy will be higher. That is the part happens at here. And this part, it told you that when you given the brighter light, this brighter light, it doesn't increase the kinetic energy. Even the brighter light, it also have more energy. But this brighter light with the more energy is not increase the kinetic energy of the electron, but it's what? Is emitted more electron. So means if you given the one light source, which is the frequency is already higher than threshold frequency, so it will emit electron faster electron, because I have got higher kinetic energy with this frequency, the higher threshold frequency. But at the same time, if you increase the brightness of this light source, it will make more electron emitted. When more electron emitted, this NE, numbers of electron emitted over the every second, then you get the higher photoelectric current. That's why it told you in the last sentences now, brighter light or the brightness of light increase, it will increase the photoelectric currents. So you see the difference here, right? So in your syllabus, you no need to know, teacher, why this high frequency light got higher energy. The energy, why they know they will be converted as a kinetic energy of electron, not the energy that let more electron emitted. And then why the brightest light more energy, and this more energy, it will be let more electron emitted, but not to let the electron emitted with a higher kinetic energy. Why this energy A to B and the C to D, why they know how, what energy they're going to convert. So this part, you no need to worry. You just need to know high frequency of light source, you got higher energy, and this higher energy, it will converted to emit the higher kinetic energy electron. And brighter light, more energy light, it will be let more electron emitted. Therefore, you got more photoelectric current, higher photoelectric current. Okay. At the same time, you still need to know, even you have the brighter light, but it's the frequency of the light doesn't exceed the threshold frequency, you still know any photoelectron emitted, then you wouldn't have the photoelectric currents. All right? The brighter light source, if frequency must be more than threshold frequency, then only you have the electron emitted. Then with comparing to the another dimmer light with the same frequency, you will have the lower photoelectric current for the dimmer light with the same frequency. Compared to the brighter light, same frequency, it will have a higher photoelectric current. Because brighter light, it will emit more electron. So this is a two different things, right, about the energy convert. Right? So hopefully you clear about that. Is that okay for this part regarding the photoelectric characteristic? Is why we keep mentioning that it doesn't depends on the intensity of light, because when we're talking about photoelectric effect, we're talking about the ability to emit electron, right? So the term and condition here, to emit electron, it must achieve the threshold frequency. It doesn't depend on intensity of light. So that's why when you learn about characteristic, talking about this. But once you get the photoelectric effects already, the photoelectron emitters, then if you want to let this photoelectron emitter to have produce a higher photoelectric currents, then you need to make increase the brightness of light source. Therefore, you can have a higher currents. So to let you easily to remember about these two different concepts here, you can looking at the solar panel. Solar panel, okay, as long as you let it explore toward the sun ray, you can generate the electricity. But to have the higher power or higher electricity can be generated by the solar panel, it must be during the very strong sun ray. So it doesn't mean that when the sun ray at the evening time or the early morning time, so the brightness of sunrise, okay, is not that high, you cannot generate electricity. You still can, but the electricity generator is very weak because the brightness of light is low. Right? No matter how, because the brightness of light is already achieves the threshold frequency, so the photoelectron will be emitted. Right? So hopefully they can understand about this concept. Yes. Okay, high frequency, Samantha, high frequency got high velocity, brighter light, high energy, more electron. Okay, so yes, you can, it's like that, but you still need to understand for the brighter light, more photoelectron can be emitted. This electron emitter is still need to fulfill the first term and condition, which is the first term and condition is the frequency of the light source must be achieve the threshold frequency. Clear? So if not achieve the threshold frequency, no matter how bright the light that you given, it still not have any electron. All right. So others all clear about this concept? Yes, please raise your hand. Yeah. All right. So when you learn, not just only memorize the keywords lah. All right. So hopefully you understand. Okay. Another one here is okay. here got a comparison emissions of photoelectron from the metal surface, okay, by the thermal emission. Just like I told you, right? Thermal emission by right, you should learn first. Okay, you should learn first in your chapter 5. Chapter 5. Okay, but we skipped that. We haven't go to chapter 5 yet. But anyway, I told you already, this is another way to emit the electron. But this one, thermal emissions to emit electron, it will take time because this thermal emissions is to emit electron from the heated metal surface. You need to heat up the metal, then the electron gains energy from the heat energy of the metal heated up, then only electron can emit. So that's why in this case, it will take time. It will take time compared to the photoelectric effect. Photoelectric effect, as long as your light source achieves the threshold frequency, when you let the metal face to the light source, immediately, instantaneously, then you get the electrons already. All right, so without any waiting time. So that's why it mentioned here, right? It mentioned about this one. Okay, comparing to a thermal emission, it will take time. But the thermal emissions, no need, because the effect is instantaneously. All right. So this term, when you go to the foundations or what, we still continue study physics in highest level, okay, it's very common to apply this term. Sorry for my pronunciations, okay, my English pronunciation is not very good. Instantaneous, okay, all right. So, and then the definitions, always, I think the SPN 2021 already asked about this. 2022 for us, 2023 got no question for paper 2, right? Okay, so threshold frequency is the minimum frequency required to produce a photoelectric effects on the metal. Right, so I think you know about this one, right? Okay, so 7.2 we stop here, right? Okay, so but you still have a one unsolved problem here. Okay, we only in this part 7.2, you only know that the photoelectric effect here, it must achieve the certain frequency, only can emit electron. So that the frequency called threshold frequency. We only know about that. Okay, but the scientists at this part unable to explain why it must achieve the threshold frequency. Why, if not achieve the threshold frequency, why the electron cannot emit it? There is no one able to explain. And then also no one can explain that why the frequency more than threshold frequency, it will be able to increase the kinetic energy of electron. Like just now I told you, right? You only learn energy. Let's say I put this as energy A. Energy A is due to the frequency of light source. And this energy A, when we increase the frequency, energy A increase, and this energy A increase, it will increase the converted as energy B, kinetic energy of the electron. So higher the A, higher the energy electron B. So A bigger, converted to the B bigger. All right. No one can explain why it works in that way. And why the A lower due to the lower frequency, then the electron cannot emit. From the experimental result is showing it's only work in that way, but no one can explain until the Einstein come out. Einstein completes the concept. So that's why we had a 7.3, the Einstein photoelectric effect theory. Right, so that one we talk later. Okay. So now, sorry for the skipping this part, the Broglie wavelength. Okay, sorry for that. Why did I skip this one? I scroll down too fast. Okay, so previous lesson we learned about the quantum energy, talking about the discrete energy packets. Okay, and then as a not the continuously energy, because from the classical theory, when look at the continuous spectrum, so the energy in this case, the energy it should be continuously, right? Because there is a continuously spectrum. But the quantum energy is what? Quantum energy is seen that as a packet of energy. So in this one, in the certain wavelength, you have this packet of energy. And this one, the shorter wavelength, you have the certain packet energy. And then this energy will be higher, this energy will be lower. So we can split energy as a one packet energy. But in the continuous spectrum, we can't see the energy in that way. The energy should be continuously energy, right? So from the higher continuously change to lower, right? Depends on their spectrum wavelength or the frequency. Okay. But the quantum energy is not seen that way. So based on that, so that's why according to Max Planck and the Albert Einstein quantum theory, the light energy is seen in the form of energy packet. So this packet energy, actually we know it as a photon. That's why certain textbook or certain reference book, it will say this photon is a light particle. All right. So this photon energy, after that we get this formula. Okay. And from the sparkings of the quantum theory, okay, there are in the classical theory, certain scientists is showing that the light actually behave a particle. Certain scientists showing the light behave as a wave. So end up in the quantum theory, it proves that light actually is a wave particle duality. So it able to exhibit the both phenomena. Okay, so what's mean here? Okay, just imagine that when you have the opening strip here, opening strip. So if a wave, sorry, if the light behave like the particle, so just imagine that we have the marbles. Okay, we have the marbles. So let's say that is a particle of light. When this marble passed through this opening, it came out, it behaved as a particle. When it came out, it's still as a particle. But if the light behave as a wave, when it came out from this narrow opening, right? Sorry, not in that way. Okay, so if there is a light particle behave as a wave, when it came out from this small opening, it will spread out. It will spread out to a large area. It behave as a wave. And it behave as a particle, then it will come out still as a particle. Okay, but the experiment is showing that the light, it can be behave as a wave. So due to that, it shows you that able to exhibit the diffraction and interference. Because diffraction and interference phenomena is a special only can be shown by the wave, unable shown by the particle. Okay, so in this case, light able to show it have a wave properties because it able to exhibit this effect. But the problem at the same time, the light also showing that have a momentum, because when it's a particle, it should be exhibit the momentum concept. Mass multiply the velocity. Mass multiply the velocity. So in 1924, Louis de Broglie, this further is not the Marsale UK or US. So that's why the name pronunciation difference. Okay. So a quantum physicist, so had put forward hypothesis. This guy, okay, it's just simply put on the hypothesis. It's just like who is that one? The chapter 3, okay, Kepler's. It's just like our Kepler's also. Right? They just simply put on the hypothesis, and then in their hypothesis, it's showing that all particles able to exhibit wave characteristic. According to the Louis de Broglie, so all the particles actually can exhibit the wave characteristic. Who just came in? Right. Good morning. Okay. Who's the one? What's the name? Left already. Don't later I see some of you enter one second and then immediately left. Or the one can consider as an intensity. Right? You got the photoelectric effect coming into my Google Meet and straight away emitted out. Okay, 1 second only. All right. Okay. So according to Louis de Broglie, all the particles means include humans lah. Human also is made by the particles one. Able to exhibit the wave characteristic. It means that if according to Louis de Broglie, when you forced to enter the nanos opening, when you came out from that, you will show the wave characteristic, which is you will be diffracted, spread out. All right, according to him lah. Just it means that it's just like imagine that talking about the soft span. The soft span, if you scratch in the span itself, if this is a sponge here, when scratching out into the nanosclip, after that, after it come up for nanosclip, what happens? It will be spread out, just like the span, right? It will spread out like this, right? So you can imagine that way. Is it human will be work in the way? Actually, according to him, yes. You should able to show the wave characteristic. However, he said that according to experimental result, it's showing that difficult to show. It's not that cannot show. It's just difficult to show. Difficult to show the wave characteristic of the particles, which is the larger mass with the larger mass. So once the particle have the larger mass, like the human, you got a very big mass. Then it will be difficult to show. Doesn't mean that you cannot show. So then the Louis de Broglie predicted that wave characteristic can be exhibited by the light particle. Why? Because the light particle have the very small mass, but actually light particle is mass equal to 0. Right. So that is a very difficult part, right? Light particle mass equal to 0, but it's still able to show the particle characteristic, right? Mass equal 0, but it's still able to show particle characteristic. At the same time, it have a wave characteristic. Okay, so for the light particle, they use something that very small mass. So example, they use an electron. So we always use the electron as our example of the photon. Okay, it's a light particle, so electron. So he stated the relationship between the momentum and the wavelength as follow. Right? So you didn't in your syllabus, you didn't learn in the detail why suddenly came out this formula. So this is the one I can't explain to you lah. Why suddenly came out this formula, right? Because according to the Louis de Broglie, right? So based on the hypothesis, it suggested this one. So the lambda equal to the Planck constant over the momentum. Okay. So based on this one, lambda equal to Planck constant over the momentum and v. So from here, what you can see, Planck constant is a constant value. Constant value. All right. So which is the Planck constant? Planck constant is a very small value. Planck constant here is a 6.63 times 10 to the power negative 34. Negative 34. It's very small value. So, and this very small value divided by the bigger mass of particle, therefore, it will even smaller. Result in what? Even small result in the wavelength. As you know, from the phenomena, diffraction phenomena, when you want to make it obviously diffracted, so the wavelength must be almost same as the opening, or opening must be almost same as the wavelength. So in this case, Planck constant is very small value. When you divide it with a bigger mass particle, then for your wavelength will even shorter, become very short wavelength. Once a very short wavelength, you want to exhibit the wave characteristic, it will be very difficult to show. It doesn't mean they cannot. It's just only very difficult. So that's why came out and then it fulfilled obey the hypothesis put on by the Louis de Broglie. Right? So then the greater momentum of the particle, the shorter the wavelength. Right? Greater momentum is one of the factor affect the momentum of the particle is the mass. So that's why bigger the mass, bigger the momentum, shorter the wavelength. Shorter the wavelength, difficult to show the wave characteristic. All right. So that's why it came out of this expression here. Hence the value of hash is very small. So particle with the larger masses, okay, it will have the de Broglie wavelength, which is too short. So, and this kind of the theory, particle unable to exhibit, or not say unable, particle difficult to exhibit the wave characteristic due to its bigger mass. Therefore, it has a shorter wavelength. And this wavelength, this kind of wavelength of the particle that difficult to exhibit the wave characteristic, this kind of wavelength we call it de Broglie wavelength. So remember, when the question came out these keywords, de Broglie wavelength, so automatically you must apply this formula to determine the wavelength. All right, so please be alert lah. And then this formula actually end up it will change as what? It will change as a MC, because we're talking about the velocity of the particle in the vacuum, which is the V here, looking for the speed of light. Right? There is the one question about this one to challenge your mind. Not easy to solve. You can try to think about it first. In the summative practice here, question 3. Right? This is a question 3. Let me see. I think the question 3 or question. Oh no, I think it's question 3. Question 3 or question 5. Both are about the de Broglie wavelength. I think it's a question 3. You can challenge this question. Right? So the answer provided behind the books. So see whether you can solve it. That one you need to express formula. Right, so that is the part. Okay, hold on. Give me a second. Okay, come back here. All right, so I think that's all about this de Broglie wavelength. Okay, and finally after that, okay, the present of the wave properties of the electron, it will be confirmed through the electron diffraction experiments. Okay, in 1927, right? So because according to this hypothesis, okay, have been put on by the Louis de Broglie on the 1924. After 3 years later, they prove it with this electron diffraction experiments. Finally, they proved that electron presented as a particle because electron got mass, and then this mass is very small. Okay, so according to the de Broglie's hypothesis, with a small mass particle, then it will be able to exhibit the wave properties or the wave characteristic. So finally, it proved already in this diffraction experiments by this electron. Okay, so and then there is a diffraction patterns electron through the thin layers of the graphite. Okay, graphite here compared to the diffraction pattern for the laser light. Okay, so and So the advantages of this electron diffraction is, okay, when we use it to design the electron microscope, it able to show even detail on the image from the example of the red blood here. Okay, for the optical microscope, we just only use the our lenses to amplify the image. So that is a view by the optical microscope, but we are unable to let it amplify into the very large, go deep into the detail. Okay, but for the electron microscope, we're able to do so. All right. So today the Samantha, okay, Lovita, and the Pan, that they have an experiment that we use a device in the so no the Pan and the Lovita. Okay, Samantha and then the group member, who else are okay. They go Samantha go to the UTM, so they borrow the lecturer use the device to see that's the example sample. They can amplify, they can enlarge the image into the 1,000 times larger. Right? So you can see the very detail, right, on the particles itself. Right? So see can up to 10,000 times. Okay, so it's able to show the wavelength is very short. This shorter wavelength is will be 1,000 times compared to a wavelength, 1,000 times shorter. Okay, so you can imagine that 1,000 times shorter. Wavelength of the light wave is about 10 to the power -7 meter. 10 to the power -7 meter. There is a range of the wavelength of light, and the wavelength of the electron can be up to 1,000 times shorter. So imagine that 10 to the power -7 divided by the 10,000 times. So it will be divided by the another 10 to the power -4. Okay, so can you imagine how short is the wavelength? That's why how difficult to exhibit the wave characteristic with that shorter wavelength. Okay, so that is about the de Bruys wavelength lah, right? So far, okay or not? It's okay. Please raise up a hand. Remember, you don't need to think about within deep why. You just need to know all is like that, is like that, all is like that. Okay, means that what you read, what you know. That's all. Okay. So now we're talking about, come back to our this photoelectric effect. We're talking about this Planck constant. Talking about this Planck constant. So you look at this activity 7.5. Okay. So in this activity, so we will repeat the step 3 to 5, which is in the step 3, we will be in step 3, we will adjust the nodes to changing the voltage, right? So when then we repeat with the from the low voltage to higher voltage, and then we read the minimum ammeter reading. So it will come out of this table. And remember, this is going to repeat by the 3 different colors of LED light, right? Orange, green, and blue. So it means that each color, so this LED color, let's say we do the orange colors here, and then we do the experiment. One set 0.2, 0.4, 0.6, 0.8, get up many readings up to 3.0 watt. Okay, continue until 3.0 watt, and then all the color recorded here. Okay, and then after that, okay, we're going to use it to plot graph. Okay, so to plot graph means that each color will have this graph. V as a manipulator's variable, right? Just now, the color is a responding variable. So then we will plot the result. Then when this one, it maybe is orange. This orange result, and then after that we will repeat. Later on we'll repeat with other colors, green and blue. So later on we will get another okay, maybe we get another one here. We get another one. This is a green colors one, and then we get another one that is a blue colors one. Okay, so later on each color we will get another different V. So we have the different activation voltage. So we have a VA1, VA2, VA3. So all this activation voltage, we will point here. So and then we plot another graph. So remember, orange color have the orange color wavelength. Orange color wavelength. And then the green color, we have the green color's wavelength. Blue color, we have the blue color wavelength. So then when we, based on this different wavelength, so we came out another table. So here is the 1 over lambda, right? 1 over lambda. This is a 1 over lambda of the orange color. So this is a 1 over lambda of the green color. This is 1 over lambda of the blue color. So from here, based on the activation voltage, okay, which is the VA1 orange colors, and afterward VA2 for the green color, and after that we have another VA3 for the blue color. So all these results we plot another graph. So from this graph, we notice that they will form a straight line, and this straight line have a constant gradient. This constant gradient m equal to the hash c over e. All right. So let me apply. Okay. So the problem here is the textbook. The textbook, it doesn't tell you why suddenly this gradients of the graph is equal to the HC over E. I repeat again, the textbook, it doesn't tell you why suddenly M equal to HC over E. It straight away told you about this one. Okay? So the question, another one, this is one question here. This is one question mark here. Why the gradient is equal to HC over E? Another question mark here is why we need to plot VA against 1 over lambda. That is another question mark. All right. So in the experiments, right? So we only have the two devices study the reading, which we will get the voltage, we will get the currents. Voltage is our manipulators, whatever, then the current is responding, whatever. So we plot the graph. So from the graph itself, we know that this is what we call it activation voltage, which is the minimum required. Minimum required to have the electron flow in the circuit. Right? Because that is the zero currents here. This activation is a zero current. Only higher than this voltage, then only you can have the electric currents. Means that only higher than this voltage, the electron can be emitted from the surface. Therefore, you have the electron flow in the circuit. So that's why we call it activation voltage. Activation voltage is the one very important for us to know about the threshold frequency. Okay, so we need to delete from this voltage, delete with the energy that we delete to the light energy, and this light energy delete to the photoelectric effect. Then from that, we try to get to know about the threshold frequency. Okay, so that is there's a concept here why we need to know about this activation voltage. The question mark here is how we get this one. Just now I already explained to you about why we need to know about activation voltage. Okay, so now we try to get this one. How to get? Okay, so as well, you know the light energy equal to HF. All right, so if there is a transfer frequency, F must be F naught. So that means that this is the minimum energy needed for the electron to emit. All right, if you frequency less than the transfer frequency, the energy is not enough to emit the electron, to emit the photoelectron. So only that achieves the transfer frequency, then you can have the minimum energy required to emit the photoelectron. So this part, can you understand? Yes, raise your hand. So you still with me, huh? All right. So don't pensan halfway, huh? Okay. So the rest not enter class. I hope that you can tell a friend up. Please, okay, go when I share the recording video, please go through the recording video. If not, chapter 7, I don't know how you're going to study. All right. So, and this energy, based on conservation energy, when we apply in this circuit, connection circuit like this, so we should relate it with the electrical energy. So electrical energy that related to the voltage, this one actually learned in the chapter 3. Chapter 3. This one learned in the chapter 3. Right, chapter 3. Right. So anyway, this potential difference, okay, we call it as work done by the charge. W over Q. Okay, work done by the charge. So this one later on you learn in the chapter 3. So now you just only need to apply this formula lah. Okay. So and then the work done here actually is the energy. So from here we will relate energy as a potential difference multiply the Q. Q is what? Q is the numbers of electron. Right? Q equal to NE. Q equal to NE. Alright. Okay. So then after that, okay, so E equal VQ, so that means that we use a hash F naught equal to the VQ. Right? So then after that, how we get this one? All this thing. So where's the lambda? So lambda, we must change it in frequency lah. So F equal to what? A equal to C over lambda. A equal to C over lambda. Then what we have here, we will have hash C over lambda. Right? So, and then this one must be equal to what? Equal to the electrical energy, VQ. Right? So EQ, so then this is, if you're talking about this is only one electron, so it will become the VE lah. And then after that, here, where's the Planck constant? The Planck constant will equal to the VQ lambda over C. Okay, VQ lambda over C. And then this Planck constant equal to what? Let's say the Q is only referring to the one electron, then it will be V E lambda over C. Oh, now which part I did wrongly? Okay. And if we rearrange this one, so we will have the V equal to the C hash over E lambda. Then there's a V equal to the C hash over E multiply 1 over lambda. This one. So then this one become the gradients of the graph. When we plot the graph, is a V against 1 over lambda here. V against 1 over lambda. And this V, according to the transfer frequency, then this one must be a transfer wavelength. So this it will become the activation voltage. All right. So that's why the gradients will equal to the C hash over E. Then after that, our hash will equal to the gradient multiply E over C. This is how we get this formula from. All right. And this is a missing part in the textbook. It wasn't explained to you why we need to plot the graph and why from the graph we know the gradients, it can be deducted, multiply with the E over the C can get the Planck constant. It doesn't explain anything about this. It just only told you need to when you plot the graph, from the gradients of the graph, you're able to get the Planck constant by the gradient multiply the electron charge and divided the speed of light. Then from that, you will get the Planck constant. So before that, it doesn't have any explanation why you can do so and how you will get the formula. So hopefully, when I explain to you, then you're able to know why lah. But don't worry, as I mentioned, actually you no need to know why. You just need to know how to use this graph. So, and then you need to know this gradients of the graph, okay, is used to determine the Planck constant, okay, which is the gradients equal to Hc over E. Is that okay? So if expression of the formula, how the the gradients of the graph can be equal to that formula provided, I try to explain to you from our fundamental concept based on conservation energy, which is based on the light energy is equal to the electrical energy, because only the electrical energy we can involve the voltage into our formula, into our experiment. So this is how we get, and then slowly we express it. Then we can get the gradients of the graph that we plot for the activation voltage against the 1 over lambda. Okay, from the graph we get the constant value. The constant value, it will lead us to get the Planck constant. Right. So that is the reason why we plot the graph. Is that okay? My explanation to you? If yes, please raise your hand. Okay. Anyway, for any one of you, if you after you device where you still having a problem, okay, please come to see me and ask, or you can ask in the group. All right. So we can have a further discussion about that lah. So if you're still a bit confused, okay. Okay, so I think this part we're done. So regarding the why the gradients can use to determine the Planck constant. So okay, so we're done for the 7.2. Okay, so now come to 7.3. It's just an extend little bit. Okay, for the Einstein photoelectric theory. As I mentioned from the beginning, why we need to be specifically discuss about this, even they are under the same photoelectric theory, just because there are some unable to explain the photoelectric effect in the concept from the beginning, right? So finally, Einstein introduced the photoelectric theory successfully that explain all the characteristics of the photoelectric effect, why it worked in that way. So finally, on this finding, he was awarded the Nobel Prize in 1921, right, of these achievements. So finally, this theory we call Einstein photoelectric theory. Okay. So Nobel Prize is one of the difficult prize to get by all the scientists. Even the Nobel Prize got many categories lah, right? But for one difficult to get the Nobel Prize is the prize only awards to the person that still alive. Still alive. So if you die before the ceremony, so or if you die before that nominated you, or the moment that make announcement, so they will cancel your qualification. All right. So because why it called prize? Why is not called as a Nobel? What is that? Nobel awards or what? Why it called prize? Because it come with the prize. They provided the money. All right. So how much money you can charge online lah? So it's huge money. Okay. So and then the Einstein explained the Max Planck idea for energy quantum. He suggests the energy carried by the light particle called photons. All right. Okay. And this energy by the each photon is directly proportional to the frequency, as I told you already. Right. Frequency of light, it will be affect the energies of a photon. Okay. So that is what we have this formula, E equal to Hf. All right. Frequency higher, light energy will be higher. So each quantum of light is called the discrete packets of energy. So only have okay. So it doesn't see the energy as a continuous energy, right? So it's a specific frequency for specific energy. Okay. Okay. There are many energy packets in the midst of light that are shine on the metal surface. So when the photon arrive at the metal surface, so the photon energy will be fully absorbed by the electron in the metal. Okay. So this energy absorbed, it will be used to let the electron emitted from the surface. Okay. And then when you provided the higher frequency, then the extra energy will become kinetic energy of the photoelectron. Okay. So usually the electrons on the metal surface will be acquire maximum kinetic energy compared to the electron inside the metal. All right. Okay. So that is suggested by the Einstein theory about the photoelectric based on the conservation of energy. According to conservation of energy, you have to remember conservation energy means that energy cannot be created, energy cannot be destroyed. Energy will be converted one type to the other type. So Einstein tried to explain the phenomena why the higher frequency will be make electron have a higher kinetic energy. So that's why he extracted this formula, which is a photon energy here. Photon energy, still remember the sound photon energy, E equal to the SF. So when the frequency higher increase, energy also increase. So when energy increase, okay, it will become what? It will become the maximum kinetic energy of the photoelectron. Okay, and then if the energy that we get is only minimum required, which is a frequency is a threshold frequency, then this one what we call it as a minimum energy required to release photon electron. And this minimum energy required to release the electron, we give a symbol as a W. This W stand for what? This W stand for we stand for work function, not trust of work. We stand for the work function. Okay. So according to this formula, so this is a metal surface. When given the light source, this is with the threshold frequency. In this threshold frequency, photoelectron is ready to emit, but it's unable to emit yet because of what? It doesn't have any extra energy converted as kinetic energy. So the time electron emitted on the surface, but it still cannot because the V equals 0. It's only emitted on the surface. Why V equals 0? Because the kinetic energy is equal to 0. And is emitted the electron here, this one we call it work function. Right? We call it work function. So there is a moment that when the V equal to 0. So when the moment this V equals 0, then this energy, it will be equal to the SF. And the F will be the work function, the threshold frequency. So the SF, this energy, call it work function. So there's a one explained here. When the threshold frequency, electron emitted without any kinetic energy. So it means the electron only emitted on the surface. So before that, electron is inside the metal. Before that, electron is inside the metal. Okay, when we given the light source with the frequency is a threshold frequency, so this electron will be come out emitted on the surface. But at the moment V still equals 0, then we have the kinetic energy is equal to 0. Right? So due to that, 1 over 2 mv squared equals 0. Then from here, we know that the W will equal to the hash F naught. So, and then this W, we call it work function. But once your frequency given, when you give a new light source, which is the frequency is already more than the threshold frequency, then you will given the extra energy. And this extra energy will be the this F will have the higher energy, which is F now. This is a new energy, which is higher than the threshold. We call it work functions. We call it work function easier. This one, which is equal to work function. So it means that now energy is more than the work function. Then we use this energy minus the work function, and then is equal to F minus F naught. So this is the one saying that when you have the F more than the threshold frequency, so when use the F minus F naught, so the extra one multiply the hash is the extra energy will be converted as a kinetic energy. So we make equal to 1 over 2 mv squared. So this is how we understand this formula. Right? Okay. And then this minimum energy that require to the photoelectron to be emitted from the metal surface, we call it work function. Right? So the minimum energy, the minimum frequency, we call it as a threshold frequency lah. So for the beginning, 7.2 we learned already. All right. Okay. So now, I want to know why we keep calling that energy when your frequency higher than threshold frequency, it will be converted as a max kinetic energy of the photoelectron. But why we keep saying that the energy is a maximum energy, maximum kinetic energy? Why we keep using this term, maximum kinetic energy? Anyone can tell me why we say so? Even in the formula also put that 1/2 mv squared. V is a maximum V. Why we say so? Anyone can explain? Why in the formula it write 1/2 mv max squared? And then the energy, we call it as a maximum kinetic energy. Why we say so? Anyone? Why we say so? Why we keep using the term maximum? Can anyone try to explain? No one? All right. So if you still remember what you learned in the last year, chapter 4 about the heat, all right, you should be able to explain that. All right. So we call it maximum because in our assumption, the energy wasn't converted into the other's energy, especially it's not lost as a heat. So we assume that all the energy is converted, the excess energy all are converted as a kinetic energy of the photoelectron. So that's why that is our idealized maximum can be achieved. Practically, when there are some energy converted as a heat, especially, then the velocity of the electron that we get, it may not as our calculation. Right, so that's why in this calculation, we have not assuming the energy loss as a heat. So that's why all the excess energy here, right, converted as a kinetic energy. So that's why I call it maximum. All right. Okay. And then for the this graph, okay, so graph 7.12 here, the Kmax against the F, right? So as you can see, when the kinetic energy here, maximum kinetic energy, when the moment maximum kinetic energy equal to 0 here, right? So the value of the F here will be the F naught. The value here will be the F naught. All right. So this one you can referring to the formula just now, which is the okay, our energy E equal to the W plus okay kinetic Kmax here. All right. So and then here is when the Kmax equal to 0, so the F will be equal to the F naught. All right. Okay. So this is how we get data about this one. Okay. And may I know if I extend this graph, I will get the negative value here. This negative value is what? What is that negative value? Is there anyone can tell me what is the negative value? What negative value is that? When I extrapolate the graph to the negative intercept here. Anyone? No one? So when you extrapolate the graph into the negative intercept on the Kmax there, the value actually is the work function. The value actually is a work function. Okay? So you see the formula, E equal to the W plus Kmax, right? Okay. So it means that the Kmax is equal to the E minus W. And what's the E? E actually is a HF minus, work function is what? Work function is a HF naught. All right. So see, this is the F. When the F, okay, when the Kmax is equal to 0, when the Kmax equal to 0, right? So your HF will equal to the HF naught, right? So it's why it means that the frequency will equal to the threshold frequency when the Kmax is equal to 0 here. When the Kmax equal to 0, your F actually, the F here actually is the F naught. So we prove it from this formula. All right. Okay. So, and then according to the this graph, where or this equation, we compare to the y equal to the mx plus c, okay, which is your y here is the energy, which is a Kmax here, and then your x is a frequency. So what's the c? Your c will be negative W, because the mx here is a HF, is a HF, right? So which is the axis x is a F, and then the gradients must be the Planck constant. Gradient will be a Planck constant. Then for the HF naught here, negative W here, actually is a negative C, which is the the work function. The work function here that we can get from the graph negative intercept. Right. So that is how we understand the formula related to the general equations that you learn in the mathematics. Right. So, and then here you see when we have the method A, method B, method C. Note the different colors of light. It's a method A, method B, method C. As I told you from the beginning, different method have the different threshold frequency. Different method have a different threshold frequency. All right. So, however, all the graph will have the same gradient because of what? Just how I already proved it to you. When you have this graph, the gradient itself actually is the Planck constant, right? Even they have a different threshold frequency, right? So, but it still exhibit the same gradient because the gradient presented here is the Planck constant, right? And when we extrapolate here, they have a different negative value. So end up means that they have a different work function, different minimum energy required to emit electron to the surface, right? So that is the way how we understand about this graph lah. I think that's all. All right. So all this I already explained to you. Okay. There is a one mistake here. This table. This one cannot be 10 power of 14. It should be 10 power of 15 hertz. If you check on the internet, the threshold frequency, it must be around 10 to power of 15 hertz. there's a range. Right? So you can try to check with this type of method on the internet. Look at the data, right? You will get it's a 10 power 15. I think this one's wrong already. Right? So yeah, problem solver using the Einstein photoelectric functions. Right, here the way how we apply the formula to solve the problem. So it's a substitutions only lah. So and this is what I told you how we use a graph. Okay, from the graph itself, you see we will study here as transfer frequency, and transfer frequency you multiply the Planck constant, we will get the work function. Okay. If you really plot this graph on the graph paper, if you really try to do, when you extend here, the negative value here, it will be as a work function. But the problem is when you plot this graph, you get the negative value here. Remember, the negative intercept here equal to the negative in the work function. So it means that magnitude itself, the intercept magnitude itself actually equal is a positive value. And when you get this result, right? When you get this result, the unit is EV, electron volt. Electron volt. So you have to convert it into the unit joule, right? Into the unit joule, right? So how to convert it into a unit joule? So you have to multiply the charge of an electron. The charge of an electron, then only you can get the unit joule, right? So if you check online, so actually, because you haven't learned about the electron potential energy, so they want to learn in chapter 3. So when you check online, EV to joule conversion, right? So you see you have to multiply charge of an electron 1.6 times 10 to power negative 19. 1 EV equal to 1.6 times 10 to power negative 19. Because you need to multiply the charge of an electron. So when you have the 1 EV is equal to 1 multiply 1.6 times 10 to power negative 19 joule. Right? So you can check on internet here, it's mentioned. Right? So if I'm not wrong, in the exam, it will provide this one for you. Don't worry. It provide this one for you, how to convert the unit. Just like the others formula here. Where is it? In the formula explain here, you see it will tell you where is the converts here? Here this one. This one you learn in the chapter 6. 1 mu equal to 1.66 times 10 for 27 kilogram. So this is one of the converts from this unit into this unit, it will be given. Only no given is the convert Kelvin into degree Celsius, Kelvin. The one is not given. All right. So and then 1 EV convert to joule, it will be given during the exam. Don't worry for that. Okay, so don't be surprised why suddenly it will tell you about the EV. Right? This is another units to present the energy of electrons. Right? Based on the electron volt. This one electron volt energy. All right. So it's still the unit for the energy. Okay, so right. Okay. Here, see this one. Even in the example 3. 1 EV equal to 1.6 times 10 for negative 19 joule. Right? Yeah, so this is still a substitution of the formula, and then this example involves the convert of the units, right? So you just read through, it's enough for you to understand how we apply the formulas already. You will notice just a substitute formulas only lah. Not this is nothing special or what. And this graph provided here just only change the axis from the frequency change to the 1 over lambda. Okay, for axis change to 1 over lambda. Okay, based on the formula C equal to the F lambda lah. All right. So when you have the same C, then the lambda will be directly inversely proportional to the wavelength. Okay, C will equal F lambda. Right, when the C is constant, so F will be directly inversely proportional to lambda. F will equal to the C over lambda. Right, so that's why we can convert this one when there's a transfer frequency, and then lambda here will be the minimum wavelength for that metal surface. So what kind of wavelength that it must be provided, then only we can have emitted the electron on the surface. Okay, So this substitution a bit complicated, right? So for today, I'm not going to discuss about this. I let you read through first. So about the change of formula. Okay, so basically just only how to play with the formulas lah. So you need to go through some example, then only you will know. Right? Okay. And then the last part here, generating photoelectric color in the photo cell circuit. Right? So it's comparing with the two different metal here, cesium and the lithium here. So as you can see, different metal have their different work functions. So when the work function is lower, means that the frequency will be the lower, right? So the transfer frequency will be lower when the work function is lower, lah, right? So the means that the wavelength will be longer, right? So the lower the frequency, higher the wavelength, lah. So that's why it's compared about these two results. Okay, and then last one, just I already explained to you. Why suddenly is talking about this light in this intensity, brightness of light, it will be affect the photoelectric circuit here, right? Actually, no affect the photoelectric effect. It's affect the photoelectric currents, right? So it's not affect the photoelectrons. It's affect the photoelectric current. It's not affect the photoelectric effect. Photoelectric effect, you're talking about how we're able to emit electrons from the metal surface. That one depends on frequency, right? So once you emitted, when you provided the brighter light, there will be more electron can be emitted. Once electron more emitted already, you want to let the electron all move with higher velocity and higher kinetic energy, then you need to increase the frequency further. Then the emitted electron will be have higher kinetic energy, right? So then if you okay, so from here, all right, so you will know that to get the more higher currents, then you need more electron. All right, so the more electron, then you need brighter light. Okay. So there are the applications for the photoelectric effect. As I told you, this is about the solar panel effect. And then this one is the generate of the electricity to the all the diffractions of the light. So this one you can check search online. I think in China they already have the 2 or 3. Okay. So all this one, at the bottom here, all are the mirror. This is not the solar panel. All here are the mirror. So that all this mirror will deflect the light, concentrate at this light sensitive method here. It will concentrate here. So you go to the YouTube, you can look at the explanation, the demonstration of the video, right? So all will be deflect the light here, and then it will able to generate the electricity with a very high power, right? So that is another future solution to zero waste energy, or the this green energy, because they're not going to release any carbon dioxide. So it's a green energy, right? But the problem is we need the very big space, right? It's not really good for the environments lah. So that's why it's only they do on the desert, right? So Sahara desert here, so there is a world largest concentrated solar power plant, right? So, and the light sensor also, the one of the example. Okay, so in this one, the emitted the light with the electrical signal used in the forming the digital image. Okay, so generate the electricity in the outer space. Okay, by the solar panel, also same. So all these are the applications in our very important in our futures lah. So that's why I think there's the main reasons why they introduce about this chapter, and let you learn about the photoelectric effect. Another way to generate the electricity, basically to let you know about this. All right. So that's all for our chapter 7. And then all the questions later on, I will slowly release the worksheet to you. And then when you do, and then after that, I will find the time to discuss as same as usual. All right. So for the chapter 7, we finish here. And after that, I will inform you another few more lessons online to finish our chapter 6. So after receive the module when the open school. So okay, don't because of the first 3 is fun learning, right? So basically, Form 5, we have no fun learnings for you. Once you go back to the class, right? So we will, I will arrange a experiment for you to do first. Then after that, our class will be conducted as usual. All right. So see you in the school. All right. That's all. Thank you.
Thank you, Mr. Ang.
Thank you, Mr. Ang.